Alright class, last video for this section. We're going to go through much of the same process as the last video, but adding one more piece to it, which is the finding the limit. So in the previous example, we got to a point where we had n number of subintervals, and at that point we just had a representation of, we could put any value that we wanted in, any number of partitions or rectangles that we divided it into for the n value. But the idea here that we're moving toward is that n is going to approach infinity to get the best representation of the area under the curve that we can. So that's what we're going to look at next, this limit process, where we're finding the limit of the sum as n, representing the number of rectangles you draw in there, is approaching infinity. So the process, the setting it up is going to be very similar. We're going to use sigma notation and then some of those formulas. So again, to save some time and space, I have this worked out, but we'll talk through it in detail. Okay, so we've got the limit as n approaches infinity of the sum of 1 plus 2 over I, or 2I over n squared, and then times 2 over n. So even though they didn't really give us a function that this went with, it's kind of a good practice, because a lot of times this is the type of question that they might ask on the AP exam, to kind of try to break this down and say, okay, well, what is it that they're getting at here? The 2 over n is representing, that's like the width of your rectangle. So in other words, the interval has a distance of 2, right? The interval has a distance of 2 because it would be b minus a to give us that 2, and then over n. And now here's the other clue in here. Well, we know that it's already been plugged into some function that they didn't give us, but the function is something squared, right? And in here, we always do f of this 2 over n, and then with the I squared, but this one actually has a 1 plus in front of it. Now recall, if we look up here at these formulas, when that's the case, that 1 that's being added there, that's actually your starting point of your interval. So we must have started the interval at 1 and then finished it 2 units down the road, which would actually be at 3. And so we'll practice that more, and then the function itself is just something squared, so it's x squared. But anyways, let's get through the process of how to come up with the limit value, go through the limit process, and come up with our area. So do some algebra, and that's a big part of this, is some algebra. The first thing, we're squaring this out. Let's get a common denominator. We can call this 1 is n over n, and so we can say it's n plus 2i all over n, because n over n would be like our 1 there. And then the width, typically that always gets pulled out in front of your sigma notation there. That can just get pulled out there. And then we'll look for other pieces to pull out as we simplify this. So as we square this, you're n plus 2i, and if we square that, you just FOIL it out, so it's n squared, and then the inner, n times 2i times 2, because there's going to be 2 of those when we do our outer and inner product, 4in, and then square the last term is 4i squared, and then squaring the denominator is n squared. Okay. Now, this n squared, since it's just one fraction, now let's pull that and put it out in front of this sigma notation, and so instead of 2 over n, now we've got 2 over n to the third, because n squared is getting pulled out here. Okay, now we're going to break up each of these terms. That's what we need to do to utilize those summation formulas. So if we do that, we are going to have we've got, and I'm pulling out, hopefully you can follow this. So I've pulled out this n squared. So really, that this isn't a fraction anymore. This n squared's gone on the bottom. But then I have n squared in the numerator. Now anything with n in it, we're going to pull that out in front of our sigma notation as well. We just want things in terms of I for when we do these sigma formulas. Okay, we can only have I or constants there. So anything else we pull out in front. So that n squared gets pulled out in front, so really we just have 1 for this first piece. Okay, the second piece, the 4in, okay, we have to pull out the 4n in front of the sigma, leaving us with just the I right there. And on the last term, we're going to pull the 4 out in front, leaving us with just the I squared. Now we can use our formulas for a constant, for I to the first, and for I squared. Okay, so the formula for the, when it's a constant, it's just going to be the constant times n, so that's just n for, 1 times n, and then we have the n squared here, so that's why this becomes n cubed. Okay, this next one, the I, that's the n times n plus 1 over 2 formula, and then the 4n is going to be multiplied in front of that, and then the I squared formula was the n times n plus 1 times 2n plus 1 over 6, and we have the 4 that's going to get multiplied there. Okay, now simplifying these, since there's a, okay, now to do this we want to have, we're going to have fractions, so we want to get a common denominator, and the largest denominator is 6. So that's what we're going to shoot for, is to get a common denominator of 6. And so as I'm going through in this next step, that's why instead of leaving that as n cubed, I'm calling it 6n cubed over 6. Okay, this piece here, there's already a 2 in the denominator, so I'm multiplying a 3 there, and I'm multiplying a 3 up top. Now here I've distributed the 4n through with this n and n plus 1. So when I do that, that's like 4n squared distributed through becomes 4n cubed plus 4n squared. So I distribute that 4n squared through the n plus 1. And then I'm going to multiply a 3 top and bottom so I can get that common 6. That common denominator is 6 there. And then here I've already got the 6. I kind of showed the work up here, the algebra. We had to foil this out, which was 2n squared. Outer is n, inner is 2n, so that's plus 3n plus 1, distributing the n through there, and then the 4 through there. Oops, I think I forgot to put n on this. Let's see here. Sorry about that, I just lost my train of thought. Oh, no, okay. So I've got that, and then when I distribute the 4, then I'm going to have 8n cubed plus 12n squared plus 4 on that piece. And I think it's going to be plus, just thinking here that I forgot to distribute this n to the last term. That should have had an n on it. And then this would have had a 4n. It's not going to affect our answer at all, because, well, we'll see why, but it doesn't matter, but that would have a 4n on it. The leading coefficients are what's going to determine our solution here, so that n that I forgot didn't really matter. Okay, so if we keep moving on here, now we can combine the numerator pieces together. So we have 6's all the way across on the bottom, and I'm going to make a note here that says look at the leading coefficients, and I'll explain that further here in just a second. But there is a lot of extra algebra that isn't really necessary here, and I'll show you what I mean. But so if we have, what we're going to see here is our highest degree in our numerator is n cubed. It's the degree 3. So I've got 6n cubed plus 12n cubed when I distribute this through, and there's going to be another term there. There's going to be plus 12n squared, and then here I've got 8n cubed, and again I've got these other terms with lower degrees on them. But all that's really important is the leading term, the leading coefficients for this. But so when I add these up, 6n cubed plus 12n cubed plus 8n cubed, that adds up to 26n cubed, and my denominator is 6. Now I know that there's other terms that would come after that, but they're really not necessary in calculating this, because if we go back and just take a look at what we did up here, I know we didn't have to find a limit here, but if we were going to find the limit of this, the highest degree here was the n cubed again, and that's the one. The highest degree here is going to always be the same as the degree in the denominator, and so that's the one that's actually going to determine your limit, because these other ones, as n approaches infinity, they're just going to become 0. So even though I wrote this to do all the algebra, these terms didn't make a lot of difference. Well, they do if you're going to pick a specific number for n, but if you're going infinity, then these just end up becoming 0. So that's why here, instead of doing the extra algebra and writing all those terms out, the only piece that's important is the piece that's the leading coefficient, in this case n to the third power, okay, in the leading term, I should say. Okay, so that's what I would have here. I have add those up, I have 26n cubed, and then the denominator is 6, and then I still have this 2n cubed out in front. So when I do the limit of this, as n approaches infinity, the n cubes would cancel out, the 2 would reduce that 6 down to a 3, and so it's just 26 thirds, and that ends up being the value of that limit. Okay, and so like I said, look for that highest degree. And then the other terms, you can basically leave those off, because as you do your limit as n approaches infinity. Those ones become 0 anyway, so you can just work with the highest degree part. Okay, so one more, okay, and similar process. This time they actually give you the function instead of just having it set up at this point for you. So our function in this case is going to be x cubed. So this is our function here, and we're using the interval just from 0 to 1, and we use the limit process to figure out that area. Okay, so we're going to do the limit as n approaches infinity, I equals 1 to n, and then I've got, now here my width, again, b minus a over n, and so that's going to be 1 minus 0 over n, so it's 1 over 0 for the width, and then my height is f of 1 over ni. All right, so that's what I've got. That's why I set it up, width times height, and those are my areas, adding up all the areas with an infinite number of rectangles. Okay, so now f of 1 over ni, or I over n, means plug that into here, into our function of x cubed. So that's I over n to the third power. And we always take this width and pull that out, or pull that out in front. And actually, as it turned out, I waited to do that because once we cube this, it was pretty easy to simplify, and then instead of just having 1 over n, we can actually pull out 1 over n to the fourth, because when we cube this out, then that'll just leave us with an I cubed right here. So this formula ends up being a little bit easier. So we haven't used this one yet, the summation formula for I cubed, which was back here. I don't think we had used one of these yet, but, and you're not going to be responsible for, you're not going to have to memorize these. You can, you can refer to them. But it was n squared plus n plus 1 squared all over 4. Okay, so that's what I'm using in that formula. Okay, so back to this point, so we've used the I cubed formula, n squared times n plus 1 quantity squared all over 4, and so now we've done this sigma notation. We've used that, so we don't write the big E in there again. We have this expression to represent that. So now we want to simplify this a little bit more. So if I FOIL out the n plus 1, I get n squared plus 2n plus 1, and if I do a little more, combining in there, distribute the n squared, I have n to the fourth plus 2n cubed plus n squared, and then over 4, and if I'm multiplying this out, now the n to the fourth goes with that 4 in the denominator. And again, so it would be at this point, if this was more complicated, I might have just said, okay, I'm just going to forget about these other terms here. I'm only going to concentrate on the n to the fourth term, because I know that that's the leading, that'll be the leading degree, and give me, worry about those leading coefficients. But this one didn't have a lot of extra work like the other ones where I had to get common denominators, so I just wrote all the terms out just to demonstrate it. But again, the only thing that's really important was the n to the fourth over 4n to the fourth, because that's what we're going to really be left with. I mean, I can still simplify these other terms and think of the limit as n approaches infinity, but the 1/4 is my answer, because these other two terms, again, are going to end up going down to 0. So the value of that, this area, is going to be 1/4 unit. Okay, and that's about it. There is one more example that I think we've done enough of these, and this one gets really complicated. There's a video, if you do have a scanner for these QR codes, you can watch a video on this one, but this one gets fairly complicated, and I think we've already hit this subject hard enough for as much as you're going to be tested on it. So that's it for lesson 4.2, and we will get on to the, probably, I think, the more fun stuff after, the easier way of doing it. This was the hard way. When you start off learning the basics of where does it come from, that tends to be a little more tedious, but got that